So our final speaker is José Manuel Corcuera from University of Barcelona. He also has a fourth name, I think, right? José Manuel Corcuera and another last.
Yeah, Valverde.
Okay.
Very long.
So he has worked on Magellan calculus, Levy processes, and even some statistics, I think. And more recently, he is working on enlargement of filtrations and the uses in equilibrium with us with information, and he's going to talk about time equilibrium today.
Well, thank you very much for the kind introduction, and thank you to the organizer for organizing this nice meeting and for this cool and cold room. Okay. I maintain the title of the talk, but in fact I'm going to talk about general properties of this Keilbach model. Let me explain for those who are not familiar with this model. This was introduced by Keil in 1982 in a discrete time setting, and was a bit later in 95 was work by Bach in a continuous time setting, even though Bach obtained also some results in the continuous time setting by passing to the limit from the discrete time to the continuous time. Okay, and then from this time, there has been a lot of papers, different papers on this model, because more than a model is a framework. So there you can, in fact, work with different models, and then there are different papers, and many of them made by people that are here, like Umut and Luciano. Okay, so it's a bit risky to talk about this here, but well, it's a risky conference. So, and then, as I told you, I will talk about this model in general, the purpose of this talk, and the work I done in collaboration with Julia Di Nuno and Bert Oxendal, is to study general properties or results that you can apply to a big collection of models inside of this framework. Okay, and the framework is, well, I will consider a filter probability space to represent the uncertainty of the market, a filtration representing the full information, and I will consider a simple market. Well, this framework considers a simple market where you have a risky asset with a price PT, market price, and for simplicity, we always consider that the interest rate is 0, and we have an horizon capital T. Okay, and then in this market, there are three kinds of traders. Let me say before that this PT is not endogenously obtained. Okay, as a result of the trading of different traders, and the traders are of this kind. We have liquidity traders, and we represent their aggregate demand by set T, and this is a fixed exogenously. Okay, this is a kind of noise in the market. Then we consider an insider that observes what is called the fundamental value of this asset, risky asset, that can be understand like the value of this asset if you have the full information about this stock. Okay, and this fundamental value is assumed to be released at time capital T, and the demand, the total demand of the insider is represented by this process xt. that is obtained endogenously, because the goal of the insider will be to maximize its average final wealth. Okay, so I'm considering that this trader is risk neutral. And finally, we have market makers that provide liquidity in the market and fix the prices in a competitive way, in the sense that these prices are this conditional expectation with respect, with respect to the information of the market makers, and the information of the market makers is given by the total demand. Okay, they cannot distinguish between liquidity traders and the insider. Okay, okay, this is the situation, and then in this context we look for an equilibrium. What is an equilibrium? Well, roughly. A rough definition could be given by this. It's not very precise, but the equilibrium is the following. I mean, given the prices, is a kind of Nash equilibrium, in the sense that given the prices fixed by the market makers, the insider strategy is optimal. You have to take into account that the insiders influence prices. Okay, and in the other direction, okay, given the strategy of the insider, prices are competitive. Okay, this is an equilibrium. Let me put an example. Even though we are worried about general properties, to illustrate what is going on, I will use concrete models. And imagine that for a moment that the demand of the insider, the strategy of the insiders are absolutely continuous, okay, and the model is such that this demand of the liquidity trade is just a Brownian motion with its variance. I assume that this is deterministic, and then the total demand obviously will be given by this expression. Okay, this is the demand of the insider. This is the demand of liquidity traders. This is the total demand. Okay, and then we look for an equilibrium in such a way that this, the prices that are given has to be given by this conditional expectation. So if prices are competitive, we have this equality. But this is the conditional expectation of this when we observe this one. Okay, so it's a filter problem. Okay, we cannot observe this fundamental value, but we observe this process. And then we want to know the behavior of this, okay? By standard filtering results that we can find, for instance, in the classical book of Lister and Sirayev, then we have, under mild conditions on this process set and V, that this conditional expectation has this expression, okay? Where this B bar is a Brownian motion with respect to the filtration Fy, okay? So, if we concrete more in the sense that we assume that the strategies are not only of this kind, but absolutely continuous, but more precise of this kind, okay? This is the fundamental value, this is the prices observed in the market, and this we assume that this is deterministic, okay? If we assume this class, I mean, we are reducing the class of some way admissible strategies in our game, and then we look for an equilibrium in this class, and then automatically, since if we consider this kind of strategies by the fact that prices are competitive, then obviously we have this equality, and then this is equal to PS, so this is equal to 0. So if we go back to the expression of prices, then we have that this term disappears, okay, and this term disappears. So what we have is just this simple expression for prices, which this lambda is given by this one, so in the end we have this relationship, okay? where this is the filtering error, okay? And what we have is this, that as a result, because of this expression, okay, and this is 0 in that case, we have that yt is given by this. So the law of the total demand is the same as the law of the demand of noise traders. So the market maker cannot distinguish. Even the law doesn't change when the insider is acting in the market. Okay? But this is because of this kind of strategy. And when this happens, we say that this strategy is inconspicuous. Okay? But this property is a consequence of that we reduce the set of strategies to this kind, and the fact that prices have to be rational or have to be competitive. Okay. Okay. Then, if we assume we didn't say anything about the fundamental value, but if we assume that the fundamental value evolves that way, where this is another Brownian motion, then we can get this explicit behavior of the filtering error. We have this relationship, and in the end we can deduce which is the value of beta, provided we know the value of lambda. Okay? But what we only know here is that lambda is deterministic, but we don't know more. Okay? So how can we obtain lambda, and what about the optimality? Because we didn't say anything about the goal of the insider, in the sense that she tries to maximize her wealth, right? So let me give an expression of the wealth of the insider, and in order to understand this expression, it's worthwhile to consider a discrete time setting first, and to consider, to consider that prices are influenced by the volume of trading, okay? And imagine that you order this, here I'm considering any trader, okay? In this situation where there is a kind of auction system where or imperfect competition, where trading influence prices. And then, if you order this amount of shares, then the price of this will be this one. Okay, it will know that this I is the index in the. It depends on on the time you are trading. Then, your wealth will be negative because you have to pay this, and you consider all these trading times. Then in total you have this, and in the end, since the value of the stock will be this fundamental value because it's released at the end, then you will have this reward at time n. So in total you will have this wealth, okay, after the release time. Then here we can do simple algebra, and then we can write I minus 1 here, and then we have this product of the increments, and this is the final the liquidation value of the set you have. And then if you pass to the limit, provided that the limit is well defined in the sense that these are semi-martingales and so on, then you will have this expression. Okay, here you can do an integration by part formula, and then in the end you have this one. So this will be the expression for the wealth of the trader. Okay, and then you want to maximize this wealth. Here, I will consider. So you will try to maximize the expectation of this guy here, and then I will consider that this is, remember that this is assumed to be I'm not sure if I say, but this is assumed to be a martingale, okay? So when you take the expectation here, you assume enough conditions to be sure that this is really a martingale, not simply local, but then the expectation of this will be 0, so I won't consider this part. So in the end, you try to maximize the expectation of this term plus the expectation of this. And the problem is how to find the optimal strategy X. Okay? But in order to know this, you need to know how the trading influence prices. Okay? And in principle, if you don't have a specific model, a concrete model, well, you can work in general by a perturbation procedure, and then, you can consider that, for instance, this functional of the volume traded, it's Frechet differentiable, which is quite general, and then you can have this representation where this is a continuous linear operator, and in the end you can write this if this is the signal measure associated with this continuous linear operator, and then by applying Fubini here, you have this expression for this kind of derivative, okay, Frechet derivative. Okay, then, you can calculate the difference between the wealth that you assume that this is the optimal wealth. You perturbate this wealth, optimal wealth, and then you calculate the difference. And by putting the expression I get before for the derivative of this, then if we assume, as I told you, that this is the optimal one, then the derivative has to be equal to 0 with respect to epsilon, when epsilon goes to 0, epsilon is 0. And so in the end we have this expression. And this has to be true for any beta. Okay? Any beta. Sorry?
This is U of W.
Yes, sorry, it's a formal notation. Yeah. Sorry. This is capital T, yeah. Okay, then we have this guy, and this has to be true for any beta, and depends on the information the trader has. In general, what we have, by usual argument, that this guy will be equal to 0, okay? And then this is the condition expectation with respect to the information of the trader, okay? And then, for instance, if the trader is such that it cannot influence the prices, then we will have that this term will disappear, and then we have this one, and then we have the prices will be the condition expectation. This is the situation of the market makers, because among market makers there is a perfect competition in such a way they can not influence because of the competition. They cannot influence prices, okay, by trading more or less, and then this is why prices, competitive prices are of this kind, okay? In general, if the information is this F, the full information, then we will have this expression. Here, this is a notation for a backward integral, okay? Because remember there was a bracket, and then I included in the integral, so this. Okay, this is a condition to be optimal, and then, so, as we have seen before, we get, in the sample I mentioned before, we get, sorry. Here, we cannot progress too much if we are in this so general setting that we have only an assumption about the functional of prices, and then we have to consider a more simple situation where we have a dependency of the volume of this kind. Oh, sorry.
Something before you go.
Huh?
May I ask you a question before you go? So in the previous slide you have this filtration G.
Yeah, well, this was just to consider, and I mean, in a situation of imperfect competition, which is the optimal trading, okay, for any trader, okay. I mean, it depends on the information you have. You have condition expectation.
Filtration generated by Y.
Sorry.
It is not the filtration generated.
No. It can be any. Okay. I mean, the filtration. This is a general result. I mean, which is the optimal portfolio or the optimal trading for in case you have imperfect competition and you have certain information given by a filtration G, which is the equation for the optimal trading. Okay, this is general. Right? I mean,
but it will depend on your alpha, right? The filtrations change when you change your strategies.
Yeah, it depends. I mean, I'm not saying anything about G. G can be nothing, or can be the information of the insider, or can be in between. This is a general result. Forget, if you know what, if you don't like this result, you simply assume that this is F, the full information of the insider. Then this is, since this is, well, you can write this as no, there is something here, I don't like it. Well, this is a martingale with respect, this is a F martingale, so you will have BT minus PT just simply. In the case of G is full information.
Okay.
Okay? In general, you will have this one. Okay?
Because the problem with this Kyle model is usually when you are given a pricing rule or price process for the market makers, the optimal strategy for the insider is not unique, so and it only depends on what happens just an instant before time capital T. So I don't know how we can characterize it before times capital T, the optimal strategies.
No, but what I saw here is that this is under no assumptions on the behavior of this price function, but just simply that is Freset differentiable, and then you have this information G, which is the optimal strategy is given by this. Okay? Any strategy of this will be optimal in a local sense because we are perturbating our optimal strategy.
If you take the strategy, if you take any strategy, and then you keep it the same until let's say T minus epsilon, and then you can just change the strategy between T minus epsilon and T, and then make it optimal.
Well, then we will discuss this later.
So you can't. So that's why I'm saying you cannot characterize it before
Okay.
T minus.
Okay. Okay. This is in any case a necessary condition. Okay. Well, then, as I was saying, we can consider a simpler framework by assuming that prices depends on the volume trading volume in this way, okay? Where this can be considered the volume of trading. This will be the lambda. This is the total demand, and I assume that this depends on time, but it can also depend on the price, okay? And it can be random even, okay? So it's a quite general pricing rule. But so far you can note that we are looking for an optimal strategy. We are looking for an equilibrium by considering certain strategies and by considering certain pricing rules. Okay? And by assuming, of course, the prices are competitive. Okay? So, obviously, we can have situations where the set of pricing rules we consider and the set of trading strategies we assume for the insider is such that we don't have an equilibrium. Okay? Or even we can have different equilibriums if we consider different, a very big class of pricing rules and strategies. Okay? Well, in any case, the definition of equilibrium is given by this one. I redefined the equilibrium because we introduced this pricing rule. But basically, it's the same idea. I mean, the price process is the equilibrium is such that given the strategy of the insider, the price processes are rational or competitive, and given the this pricing rule, the strategy is optimal. Okay, this is the equilibrium. Okay, then we have this result. Okay, that a necessary condition by using the same arguments that I said before. We have this equation now, okay? It's a bit different with respect to, because instead of having this Ferchet differential, we have this partial differential with respect to the second argument, and here appear this lambda process, and mu t is given by this one, okay? That takes into account the dependency of lambda with respect to prices, okay? And we have this condition to be optimal, okay? That this can be deduced from here, when t goes to t, okay? Then this goes to Vt. The difference goes to 0, okay? And then remember that this is a marginal, okay? So it cannot have a jump at capital T, okay? Okay, because we didn't say anything about Vt. I mean, Vt can be a marginal, but can have jumps. Eh? Okay. What else? Okay, if we and we have also this corollary. Okay, and this is important. That is, we have an equilibrium, and we have also, and we have that this is different from 0. Okay, almost really in this interval. Then we have that this is marginal, an Fy marginal. Okay, and this is quite interesting because we can apply this general result, for instance, to our first example, because in that case lambda was deterministic, and then this is equal to 1 because there is no dependency on prices on lambda, and then what we get is that 1 over lambda that depends on t in principle has to be a marginal, so it has to be a constant. Okay, and then from this fact we can deduce the expression for lambda in the problem we have now, and then we can deduce the value of beta, and this gives the optimal strategy for the initial example. Okay. Okay. What else? Well, this is the proof, but the proof is the same idea. I mean, this is a proof of the theorem and the corollary I mentioned, but the idea is just the same as before. I mean, to consider that you are in the optimal strategy and to perturbate it and to take derivative equal to 0, and then well, you get the same. The only thing new is that you have a dependency on prices in lambda, so you had to calculate the derivative of prices with respect to epsilon, okay? And then you have a kind of, you have an equation here, and then if you solve it, then well, you have that the solution is given by this, okay, and that's all. Okay, and then you recover, but maybe then you have this expression that is true for any beta. So in the end, the conditional expectation of this guy with respect to the information f is equal to 0. Then you have the equation. The interesting point maybe is how to get the corollary. I mean, this fact that eta t divided by lambda is a marginal. It's just to do an integration by parts. I mean, in principle, you have this equation. Then, well, just simply lambda was here. I pass to the other side, and then it's just simply to use this integration by part formula. Okay. And to calculate which is the differential of this, and then you arrive by using the definition of eta and lambda, and you arrive that this is absolutely continuous. Okay? And then this is 0, and then you can put here this differential and so on, and then you have this expression by using the integration by part. You plug in the condition to be optimal. And then, well, you get this one, and then you separate. This is the point. You separate in a part that is a marginal and the part that is a Bundin variation. Okay, part. And then if you do this, then you have well, this is the equation you get, And then, you, as I told you, you can separate in the boundary variation part, and this is this part is a martingale. And then when you have this equation, okay? And then if this is different from 0, then this second derivative is 0. And then you go back. Remember that the differential of eta divided by lambda was basically this, multiplied by something. Then since this is 0, we have that this is a constant. Okay? Then you have that this is a trivial martingale in this case. Okay? In other cases, can be not trivial martingale. Okay. Then, well, this is in this particular case, it's curious that since this is a constant, the quotient between eta and lambda is a constant, then you can obtain the expression for the prices. And remember that the second derivative of lambda depends on p, the prices. Second derivative is 0, so it's linear in p. Okay? So you have that this is equal to this expression, remember the expression eta, and then you have this, and then you have, depending on the values of d, is different from 0, then you have the Blackstone's model of the Vasily model. No? It's curious, okay? Okay. Then we have this result that has to do, I think, well, it's a bit curious, because in some sense it's against the result of Bach, in the sense that if we consider this kind of price functions, okay, where this sigma is not necessarily the sigma of the noise in the market. I mean, this is a variance of the Brownian motion of the liquidity traders' demand. Then that is assumed to be deterministic here. Then if we have this class of pricing functions where you have this relationship, this is different from 0, okay? Then you have the result that you have an equilibrium if and only if this happens, okay? And then, well, there is something new with respect to back result is that the martingale part, because here, what I didn't say, I should say, but I didn't say anything about the classes of strategies I'm considering in this.
The sigma here is the noise traders volatility.
Sigma Z, yes. And this sigma is a pricing rule, a class of pricing rules chosen by the market makers.
Should be the other way around.
Yeah. No? Should be equal, no.
So sigma Z is the...
Sigma Z is the volatility
of the insiders.
Of the liquidity traders. Liquidity Z is the demand of liquidity traders, remember. And then I'm considering here that it's a martingale, and this is the volatility of this martingale. But basically, it's a problem.
You should be having sigma Z in the PD for H, right? H is the one that is chosen by the market maker.
Yes.
But you're using sigma over there.
Yeah, but it's not a sigma. It's a function. I consider this class that market maker decided to use this kind of rules.
Yes, but H has to be H of TYT has to be a martingale, right?
No. Yes.
Yes.
Yeah, because prices have to. But then, as a consequence, you have that this is not a martingale, but this one. You have a certain drift. In case that this sigma is equal to this, then this disappears, because this is 0. Okay? But the curious thing is that here you can have a strategy such that the martingale, the continuous martingale part, because I am considering strategies that are of this kind. Basically, it's an Ito martingale in an absolutely continuous process plus a continuous martingale and plus a boundary variation unpredictive process with jumps. Okay? Jump process. Okay? Because the strategy has to be predictable. Okay? But in this kind of strategy, well, you had to add moment conditions and so on in order to give meaning of all these guys here. in the integrals and so on. Okay, but in this condition, then you have this result. Okay, this is an if and only if.
Okay. I mean, so if you look at Beck and Peterson, then they take lambda equals 1, I think, right? So they don't do any scaling.
Well, they consider lambda a constant. Yeah.
Yes, and then they have the noise traders.
Now, in the case of Bach, what's happening is that this sigma is equal to d, because one statement of Bach is that I think is wrong, is that he said that the only statistics that produce an equilibrium, in the case that this is, in the case of model of Bach, that's where this is deterministic, and then you have a Brownian motion with this variance. And the only equilibrium prices, rule prices, are given by solutions of this equation with this sigma equal to this one.
Yes,
and this is not correct, because
doesn't matter. And the inequality is reversed. So you should be having the volatility of the insider signal larger than the volatility of the merged trades, so that there is an equilibrium, because insider has to have an advantage so that he has less uncertainty. Otherwise, you can't have an equilibrium. And also, Beck doesn't assume that the second derivative is not equal to 0, so you don't need to assume that.
Well.
So you are actually putting much.
What's happening is that you can say this if you have this condition. If you have the condition this is equal to 0, and then you have a linear function, then you have that this is 0.
Sometimes it is 0, sometimes it is not. You can't have this one.
Yeah, but if you have that
doesn't mean H is linear.
If you have a situation where sometimes, it depends if this happens in a set that with probability different from 0. If you consider with measure different from 0, you consider the measure given by the probability and the Lebesgue measure, the product. Okay? And in this case, then you can say nothing. In the case that this happens, you can say this. In the case of linear case, you obtain that this is 0. Okay? But
Beck doesn't consider only the linear case. I mean, he considers all types of things. So he doesn't need any condition on the second derivative.
No. In the back consider a function h.
Yeah. So it can be any function. It doesn't have to be linear.
No.
Yes.
No. But okay. Good. In the case that sigma is equal to this one, then you can obtain a more general result. You don't need this condition.
Yeah, but you can take signal to be equal to that, because you don't need lambda. Because when you have a Gaussian signal, all you need to do is just Kalman filtering. You don't really need to do it. And H can be anything.
Which can be anything?
H can be any function of the demand. And you don't need to consider any scaling by lambda.
No, but lambda.
Because everything is just Gaussian.
Lambda doesn't play any role here because it's a constant. You assume that this is a constant here in this case, in this theorem. Okay. Then what I say is that if you consider this different from, sigma is different from sigma z in general, then you have this. If sigma is equal to sigma z, and this is 0, then you get the result of Bach. Okay? But Bach says that the only class where you can find an equilibrium is this kind of function with this sigma equal to this one, and this is not true.
That's true up to a scaling. Once you scale, and then you get something else. So I don't think that's such a big deal.
Okay. Well, in any case, if you have this result, then this is an example where this happened. I consider this kind of rules, okay, that satisfies this with a different sigma, different from because I'm considering that here that the noise, the sigma is constant, okay, but here appear another, alpha is different from 0, okay, yeah. So it's the case of before, and then you consider this kind of strategies with this quadratic covariation, then you have an equilibrium. So it's an example where you have strategies with a continuous marginal part, but it is not suboptimal, but optimal. So in this sense, it's because in the back, let me insist that.
We can talk about trade-off because unless you, so when you allow scaling in the demand, unless you put some penalties, actually the insider can make infinite profits. This is not something in the literature, yes, but that's it's true. So
no, I don't know.
So this is so you have to put some cost.
But it's not. I think it's not a problem for scaling.
No, it has nothing to do with the scaling. This one has nothing to do with scaling. But if you allow the pricing rule not just be a function of the total demand, but if you allow the pricing rule to be a function of the scale demand after this integrating by lambda, you can find strategies of the insider that gives an infinite profit.
Well, I don't know, because in this case we assume that it's constant. Okay, so in general, I don't know what happened.
The constant case may not matter because you can just divide by this constant and then get rid of the constant. I don't understand why is it.
Yeah, well, I understand what you're saying. Yeah. But this is another story, in my opinion. Okay, well, let me see. Okay, then you mentioned largeness of filtration, and then let me say something about how enlargement of filtration enter in the problem. Okay, it can be seen that if the strategies are absolutely continuous, then optimal strategies are such that the total demand is marginal. Okay, and then at least if we consider a certain class of rule functions, okay, rule price functions. Okay, then we have this equality. This is the strategy of the insider. This is the demand of the night trader. This is total demand, and then this is a marginal, and then this is also. But this is the martingale for the filtration Fy, a martingale with respect to this own filtration. But this is a martingale for the filtration of the insider. Because the insider, I told you, this is observed as martingale. And then this can be seen as a canonical decomposition of this martingale when you have this information. Okay? But the problem is that and then you can use enlargement of filtration result. Okay? But the problem is that the results in the enlargement of filtration is that what you had normally is that a process minus certain drift behaves like Brownian motion or something like that. Okay? But in this case, what is fixed is this one, not the process Y. Okay? So what you have with this enlargement of filtration techniques are weak solutions to this problem. And then you had to pass to strong solutions by, for instance, using Yamada-Watanabe theorem. So, okay, this is the. But I consider that the main problem. Well, there are different problems in this framework, but the main problem is not necessarily, as certain authors say, to find the optimal strategy. Because, well, optimal strategy will be interesting for the insider. But we are interested in the behavior of prices when there is an insider, for instance.
But if there is no optimal strategy, then there's no price. Right?
Sorry?
There has to be, for an equilibrium, you need both sides, no? You need the optimal strategy as well.
Yeah, you need to, but you need to show the existence of an optimal strategy more than the concrete. I mean, this is interesting for the insider, which is the optimal one, but for the rest of people, what is interesting is the behavior of prices in this situation. Okay, so how it behaves lambda and which is the behavior of the pricing rules. So, okay. Well, this is an example where you can use these enlargements of filtration results. Okay, I'm not going to insist in this way. I mean, this is very well known. I mean that if everything is Gaussian here, fundamental value, that in this case is constant, and the release time is 1. This is the demand of the traders, and lambda is constant, equal to this 1. Okay, and then if we have this situation where this y behaves that way, then this minus this behaves like this one. Okay, and then from this is a very well-known result. And from this we have that this is the solution for the optimal strategy. Okay, for at least for a strategy that produce competitive prices, but it can be seen that satisfies all the other conditions in the sense that prices go to the fundamental value. Okay, this is a necessary condition. Well, and then we can give this form to the strategy. Okay. Okay. What else? But what happens if another problem that we have considered is what happens if the release time is random? Okay, because so far time was deterministic. Well, in this case we can do the same, more or less the same, and we have to do this expression. Okay, that now tau is random. Okay, and this is equal to 0. Okay? And well, we can consider different situations. We can consider a situation where tau is known to the insider. In that case, the result we have are similar to the case that we have a fixed horizon. And fixed horizon, and then we have this result. I mean, prices goes to the fundamental one. We have that if this is fulfilled, then this is a marticle, and so on. And this can be also true if tau is unknown to the insider, but the stopping time is predictable. If the stopping time is predictable, then we can put here the sequence of announcing times, okay? And then we have the same result. I mean, this prices converge to the fundamental value, okay? But what happens if it's unknown and unpredictable? In that case, there is not a general result, okay? We have results, for instance, if tau is independent of the rest of processes involved in this game. In that case, for instance, a partial result is the following. If we have that this has a density for any value of t, I mean, this is strictly positive. For instance, imagine that tau is exponentially distributed. We have this one, the prices converge to the fundamental price, and this is also, and if this is different from 0, then what we have is, and this is a change with respect to the case that horizon was fixed. What is a martingale is this one, okay? And this is a survival probability. And, well, this is a general result that can be applied to concrete models. For instance, in the case of the example of Bach and Baruch, they considered that tau was exponentially distributed with this parameter r. And then, well, this is the equation we have for optimality. Then we can use the same argument we did for in the proof, an integration by part formula, and then if we follow the same steps, we arrive to that this is absolutely continuous, in fact, and it has this expression. Then you have this equation for lambda. That is exactly what is get for this particular example in this paper by Bach and Baruch. Okay, but this is the application of this general result to this example. And another application is in this example of Colin Dufresne, where they consider this kind of strategy for the insider, where beta can be random, okay, because they consider that the demand of the noise trader is the volatility is stochastic, okay, but this process is independent of the rest, okay, the process is involved, and then well, they also assume that this is this V fundamental value is Gaussian, okay. And if we apply this, well, we have this relationship because of filtering results. We have this relation between lambda and the filtering error and beta and so on. And then, well, the problem here is, remember that we solved the problem at the beginning by a similar problem, but we had that this lambda was constant. In that case, it's not constant, but random. But then how can we solve this problem? Well, we know that 1 over lambda has to be a martingale, okay? And then if we look for this solution of this kind, with this sigma t, this is a process that we have to determine. Then we know that this 1 over lambda is a martingale. Then, well, we can get the expression for sigma t is given by this in terms of this new process G. And then if we calculate this differential, then we have this relationship, and then we know that this is a martingale, okay? And in this case, this is not only local martingale, but a martingale, a real martingale. And then, well, we can, and on the other hand, because sigma t goes to 0, when t goes to capital T, then we get that this has to behave that way. This has to go to 0 as well, okay? And then we have this relation, this equation, and then if we take gt is equal to 0 because sigma t is 0, and then we have this equation for just taking the conditional expectation here, okay? And again, it's a general result applied to this one. And let me finish with a controversial example. This is another case with random horizon, and then, well, the fundamental value in this case is not constant, but evolves that way. This sigma is deterministic. These are independent Brownian motion. And then we assume that the release time is exponential, independent of all these guys. Then we know that by the general result that it has to be a constant, because it has to be a martingale in general, but in that case it's a constant. And then from this, because this is exponential, then we know the expression for this. We can obtain the expression for lambda. And then what? Well, we can assume that this is constant. Well, they consider this case, and then we have this expression for the filtering error, and then we deduce this beta, the value of beta, and then we can obtain lambda 0 from this condition, and then we get this expression for lambda 0. Okay, this is an equilibrium, but you have to assume that this is finite. Okay, if this is a constant, for instance, this doesn't work because this is flow. Okay, and what's happening in this case? In this case, and in the case that this is a constant, so this is not a solution, it can be seen that you can try to find a solution in in this class. I didn't, well, in the class I mentioned at the beginning, beta multiplied by the difference between the fundamental value and the market price, and we can try to find a solution in this class of statistics such that the filtering error goes to 0 when we approach to certain time capital T, okay, and then is 0 after this, okay. If the filtering error is 0 after this, then the statistic cannot be absolutely continuous because you have to kill the Brownian motion in order to have that the prices and the fundamental value is the same. Okay, and then it's I mean in this case, okay, that this is constant. We look for a solution of this kind, that this is 0, the filtering error for t greater or equal than certain capital T time, and then the prices are equal to the fundamental. But this implies that from this expression for the sigma t, you can deduce which is the value of t, okay? And then still we need an additional condition to find the value of lambda. And then if we put this transversality condition, that can be justified because this gives the optimal time, capital T, for the expression of the well of the insider, then we get this equation. And after T, we have, what you have at the capital T, what you have is that the expression for the strategy of the insider is given by this, and this is not absolutely continuous anymore. So this cannot be well. This can be interpreted as a limit of strategies. Okay. That approach a limit of absolutely continuous strategies that approach to a non-absolutely continuous. If you consider this kind of limit strategy, you can assume that this is a kind of equilibrium in the limit. Okay.
But if the filtering error is going to 0, doesn't this mean that you just know the value?
No, but what do you mean?
What happens at time capital T? So at capital T, I thought you were saying...
No, capital T is you obtain, if you consider a strategy of this kind, as I told you, the strategies that are absolutely continuous of this form, beta multiplied by the difference between fundamental and the market price, and then the prices, you take beta such that prices go to 0. The filtering error goes to 0 in certain time, capital T, that you have to find in an optimal way. Okay, then you have this equation for T.
And by filtering error, you mean the difference between
beta and between VT and PT. Okay? Then you can find
PT.
Yeah. The fundamental and the market price.
Yes, so at time capital T, VT is equal to PT.
Exactly.
I see, okay.
Exactly.
And then you want to follow...
Then you have to follow... this is, as I told you, this is can be seen as a limit of... it's not just generalization of equilibrium. Okay? Because it's not exactly an equilibrium, but it's a limit.
Okay. It doesn't really matter, because after time capital T, VT minus PT is 0. So you don't make any money or lose any money. So you don't care. No?
Yes, this is the point. This is the point. When it's not the same to consider the limit and to consider the strategy of the limit and to consider the expression of the wealth for this limit strategy, that to consider the limit of the wealth when you approach to the limit strategy. It's not the same because of the quadratic variation.
Yeah. No, but what I meant...
there is a profit, even though...
No, what I meant to say is you don't really need to do any approximations because the fact that you need to use absolutely continuous strategies depends on the assumption that P and V are different. If P and V are the same.
No, but it's not what you go is what you do is to approximate more and more to the situation where V and P is the same. If you are going to this strategy, but starting with absolutely continuous strategy, then there is always some profit, okay? And then you can, in the limit, to get the optimal one. Okay? Well, this I will finish with these references. There are many references about this problem, but these are the references that you can use to understand what I say, okay? Well, this is under... No, it's okay. No? No. That's all. Thank you very much for your attention.
Any questions? I have another question. Because you're using the fact that this, the insider strategies are mediating the differential between the right? But that's not always the case, because if you have, this is not going to be always the case, right? So because here you're assuming you are in a Gaussian framework.
Well, in a Gaussian framework, you
in a Gaussian framework, yes, that's not what happened. But
I don't know, but in the result we consider it are general. I mean, the strategies, the set of strategies is strategies that have a naturally continuous part, a continuous marginal part as well.
And then what I meant is like if the insider signal is a general macro process, not just a Gaussian signal,
then you
wouldn't have.
I don't know.
José Manuel again.